Thank you very much for this kind introduction and the invitation. It's a great pleasure to speak here today. I'm going to be presenting a talk on permission decentralized ledgers and the governance of money. It's together with Cyril Monet from the University of Bern and Hyun Song Sin from the BIS. I want to remind everybody I'm always speaking on my own behalf and not on the behalf of the BIS. And when we think about sort of the topic of today's conference, right, the timing couldn't be any better. Digital currencies of all kind are in the limelight. Bitcoin is near an all-time high. Ethereum just launched its 2.0 beacon, and Libra is making big waves just by changing its name. As a central banker, for me personally, and I'm very happy that we just saw Geoff's nice presentation on this, that I'm the most interested in the massive wave on research and development of central bank digital currencies we've seen during the course of this year. We've seen a number of major central banks launching reports, including the Bank of England, the Riksbank. The BBC has launched an extensive pilot, and the Central Bank of Bahamas has even issued a CBDC. And many, even if issuance of CBDC has not been decided in any of these jurisdictions other than the Bahamas, it's important for the greater public debate that central banks line out how a CBDC could look like and how it would affect the economy. This is what we've done in the BIS Innovation Hub, together with 7 major central banks. We've lined out the core functionalities and principles for a CBDC issuance. And I think all of these developments taken together have been summed up well in a speech by Bank of England Deputy Governor and Chair of the CPMI, John Cunliffe, which was titled, "It's Time That We Talk About Money." And when we talk about money, we need to foremost remind ourselves that money is nothing more than a social construct, a means of society to simplify economic interactions. Ultimately, we don't want money, but we want to consume goods and services and invest in real projects. But there are millions of different goods and services, and without money, we would need to deal with a complex net of bilateral economic interactions and IOUs. Money simplifies the comparison of prices. It is the yardstick of economic activity. As Narayana Kocherlakota put in a seminal paper in 1998, money is society's memory of economic interactions. To know how much you can consume, you don't need to remind yourself of your employment and consumption history. You just need to look at the balance of your bank account, and you know what that means in terms of what you can afford in the future. And because money is a record-keeping device, advances in information and communication technology have continuously transformed its form. From stone wheels to coins, from coins to banknotes, to the rise of centralized accounting and commercial banking. Now, today, we're at the moment where this advance could continue and centralized accounting could transform into decentralized accounting. And of course, that already exists in practice for over a decade in Bitcoin and related cryptocurrencies. A blockchain is a public record of who owns which token. Of course, here, who could be a pseudonym rather than a person. And a payment is merely the transaction instruction that changes ownership of a specific coin from pseudonym A to B. And in the same vein, in a later block or a later page of the ledger, user B might transfer that token to C. The blockchain is the public memory of this cryptocurrency ecosystem. But of course, everywhere where there is value, there is the danger of fraud and theft, and this needs to be overcome. The key issue in cryptocurrencies is how the blockchain is updated, which happens via costly computing or proof of work. Because the latter makes updating of the ledger costly, it also makes forgeries costly. So proof of work works, has a history of working, but it has some drawbacks. First, it comes at a horrendous economic cost and has a substantial CO2 footprint. Second, it does not provide certain finality, and indeed, smaller cryptocurrencies have already been attacked. Third, As a ledger that is public, it axiomatically cannot offer full confidentiality that many would want in payments. Because of these drawbacks, institutions around the world have been experimenting with a variant of the technology, so-called permission DLT. Here, rather than an anonymous network of miners, a network of predetermined and known validators augment the ledger. Insofar as these validators are known and form an exclusive set, this permission DLT lies in between the extremes of a centralized market and permissionless cryptocurrencies. Superficially, the structure of these systems is very similar to a cryptocurrency setup. User A initiates a transaction, a set of validator reads it, and once they agree that it can be included in the ledger, the token is transferred. But underlying the economics and functionalities of these systems are quite distinct from the Bitcoin setup because they do not involve brute force computations. They could potentially be much more efficient. And this, has made many think about how to use it in payments. It has received attention in stablecoin proposals, such as the project formerly known as Facebook Libra, as well as in CBDC proof of concepts. In a recent study with my colleagues at BIS, we actually find that the majority of CBDC projects and cross-border payment experiments is based on this technology. The assessment so far is that the technology works, but the advantage over existing payment systems needs to be demonstrated. As my general manager, Agustin Karstens, had put us in a speech, for a central banker, it's never about fascination with the technology per se, but about knowing whether it can be put to economically good use in mainstream application. Now, that is still an open question. And the focus of this paper that I'm presenting today is to dig deeper into the underlying incentives and the economics of the governance of such systems. So what do? We build on a sizable and growing literature studying the economics of permissionless cryptocurrencies. So in economics, we've seen some important studies that highlight the cost of proof of work. For example, my paper on the doomsday economics of proof of work takes this analysis a step further and argues that sort of the long-term viability of many cryptocurrencies cannot even be taken for granted. Surprisingly, on the permission variant, there's very little analysis in economics. There's ample practical work in the computer science community with a variety of supermajority voting processes being proposed, but none that look at the underlying incentives of these validators. And this is a crucial issue. We want to take eventually a permission DLT setup out of the laboratory environment and use it in at-scale applications. And we need to understand the equilibrium properties of these systems. And that has to date not been done, except by a work by Bruno Bier and his co-authors who study the robustness of such schemes when there are Byzantine agents, i.e. malicious attackers. And what we do is we contribute to this literature by building a theory of permissioned ledgers. The main question that we ask is, who will guard the guardians? Validators may be known, but they have their own objectives, and nothing can prevent them from abusing their privilege. Specifically, in the permission context, validators need to have incentives to do their job, i.e. to verify transactions and ensure that all transactions and no invalid transactions ever enter the ledger. Incentives need to ensure that validators actually put in the effort needed to do all these steps. And second, that they never accept bribes to undo certain transactions ex post via the equivalent of a double spend attack. We study these questions and ask whether, from an economic perspective, it actually even ever makes sense to set up a market in a decentralized way, i.e. with more than one intermediary. Along the way, we also study the optimal design of DLT. We examine the optimal supermajority rule, and we determine the optimal number of validators. Let me give you a preview of what we find. First and foremost, we do find that there is a case for decentralization. The fundamental case is simple. Honest record keeping is made easier if those who actively participate in the system as a user also occasionally are in charge of updating the ledger. However, this does not come for free, as we show that with multiple validators, there is a coordination problem. Validators play what in economic is called a public good contribution game. If there is some uncertainty, for example, brought about by communication outages, the optimal voting rule must be structured so that it is robust to these aspects. So with many validators, high rents need to be validators need to be coordinated, and this requires high rents and a supermajority voting rule. Second, for the efficiency of these systems, the degree to which agents are forward-looking matters a great deal. Intuitively, the system cannot avoid misbehavior, but it can punish it by exclusion in future rounds of this system. So the more the future matters, the easier it is to incentivize truthful record keeping. However, a surprising result emerges in the comparative statics. We find that the case for decentralization is the stronger, the more difficult it is to sustain honest behavior. So this is counterintuitive, right? We find that the new setup, the decentralized setup, is actually the most useful in the cases where trust is the most difficult to attain. The underlying intuition harks back to the basic insight, the fundamental case for decentralization. It is precisely in instances in which the central intermediary is tempted to cheat that a decentralized setup with many who have a stake in the system who want to keep it alive and thus have the right incentives to withstand the temptation to cheat. Let me put this in a model. Let me go to the model setup. So we're going to build a credit economy with discrete time and a discount factor beta. Each period has two production stages, and in each stage, a good can be produced. And there are three types of agents. One type are those that can produce the early good. And there are two classes of agents that pose as if they could produce in the late good, in the late period. A measure 1 minus f actually can indeed produce the late good, but a measure of f is faulty and actually cannot produce. Late and early producers meet, and importantly, without the help of an intermediary, the early producers cannot tell whether he's facing an actual late producer or a faulty bad one. So in this economy, if there was a way to force everyone to behave optimally, faulty producers would simply leave the market, and other matches would work out as follows. In the first step, a producer A produces at some cost, minus X, and sends the early good to B, who consumes it, obtaining utility U of X. There is a net gain in that, as B's utility is higher than A's production cost. In the second stage, B produces the late good and repays A for her services. But of course, absent some form of commitment, the question is how we can attain this outcome, how we can convince B to pay back. This brings us back to the title of my presentation today. We need a collective form of memory. We need a record-keeping device. And this is where the ledger comes in. The ledger records past behaviors, actions, and outcomes. To the users, the ledgers is not known. We want to have privacy, confidentiality in that setting, but the validators can read and verify it at some cost, and they can also update the ledger with new transactions, again at some cost. Let me note that the validators are drawn from the late producers themselves. This is an important ingredient of the model, and in fact already an anticipation of the results. We want to solve the incentive constraints of the late producers that have to repay something and they can't be forced to doing something. It will be optimal to choose the validators from exactly the set of producers that is causing the fundamental problem, because that gives these validators the right incentives to behave optimally. So let's look into the exact game of validation. Validators need to observe all actions and write an honest account of what happened into the ledger. Production can happen at an early, at a late stage, but to get down to the bottom of the economics, we simplify and assume that validation incurs costs only in the first stage. There is a cost CV to verify the label of A and B, and there is a privately known cost to communicate the vote to the ledger. And we allow for this cost to be stochastic, reflecting the fact that in reality, there might be communication outages and other operational issues. Whether the validator's votes make for a valid ledger update depends on the rule of the consensus algorithm. Here, what we focus on is the class of consensus mechanisms that are based on supermajority voting rules, where a ledger update is considered valid if a fraction larger than tau approves of an entry. We will endogenously derive this tau later, but let us take in for given as a moment. So if validators do their job correctly, the game now proceeds as follows. All validators read the labels of B. They see B is good, so it's not a faulty producer. They send their vote to the ledger. A then actually produces for B. B later observes that he has received the X from A, he has consumed it, and he pays back in the second production stage by in turn paying back to A. And the final step is that the validators observe all these actions and they say, yes, the game has proceeded as intended. Both A and B keep their good label, and the next round continues. However, again, we haven't really solved the underlying economics. We've just described how things would play out if everyone behaved well. But there are underlying frictions. And now the frictions is why validators should honestly record what actually happened. One constraint is that agents could bribe validators. And another one is that they could aim to free ride on the effort of other validators and just vote along with the majority without ever actually putting some effort. Let's look at these in turn. Let's first go to free riding. It would mean that validators would fail to detect that B is actually a faulty producer because they actually didn't monitor. Importantly, there is an important coordination game here, as validators can only be punished based on deviations from the majority of others. Nobody knows what is the actual truth. We only observe the majority of votes. So if validators assume that all other validators will shirk, they likely will not put in any effort themselves, because the majority vote might not reflect the truth, and there is no value to find out the truth on your own. For game theorists and those working on stochastic outcomes in the presence of such complementarity in actions, this is a well-known problem, and it can be solved in a global game approach. In such a setup, all validators follow a switching strategy where they will work for sure if their cost is below a certain threshold. A well-known equilibrium property is then that even for a very small amount of noise, a unique equilibrium can arise. So we solve this game based on this global game approach methodology. It is really about dealing with higher order beliefs, where it's not only about what I think what others will do, but also about what others perceive that I will believe about their action, and so forth. And we suppose that all validators follow a switching strategy where they will work if their cost is low enough, and they will shirk otherwise. And we solve for this cutoff point that makes a validator be indifferent between shirking and working. This cutoff point is determined by the following incentives. The validator who is indifferent between shirking and not, it has an expected net payoff that is equal in both scenarios. The payoff of shirking is 0, whereas working first entails paying the verification cost, CV to find out the label. A fraction of labels 1 minus f is good, and then the game continues. And if that is the case, the validator will also communicate production at cost C. So he does that for sure. But there is only a probability that all the other validators will actually go along with that and also communicate and do their work. Importantly, due to the precise setup we adopt and the fact that the distribution of these costs is uniform, this means that the probability that the supermajority is exceeded is equal to 1 minus tau. If the supermajority rule is high, it is unlikely that the consensus goes through. The crucial insight regarding the optimal supermajority voting rule is that a voting rule that is close to 1, i.e. that requires unanimity, makes it more and more likely that the supermajority is not reached, and consequently, it's less and less worth it to put in the effort for each validator privately. This is one side of the coin, and the result is that to get rid of the free rater problem, the supermajority needs to be low in order to overcome it. But there is another side, another problem, and that is the bribing problem. A high supermajority rule makes it easier to overcome the fact that validators can be bribed. And what happens in the case of a bribery is that B, although A produces in the first stage and hands over the early good to B, B then does not repay. He doesn't actually repay. Instead, he pays a bribe to the validators. And this is the exact same thing as a majority attack or double spend attack in a cryptocurrency, where you first see a transaction and then it is removed by the miners. And here it's the same logic, it's just performed by the validators. Crucially, although nothing can technically stand in the way of such an attack, it is detectable, and false updating can be punished by the exclusion from the set of validators and producers in future rounds of the game. So these are the essential trade-offs of the game. Many validators make it cheaper to overcome the bribery issue because the fear of being kicked out as both a user and a validator disciplines behavior. But many validators imply that the free riding problem in the first stage is more severe. So with any degree of noise, a supermajority is needed that is strictly below 1. And the higher the supermajority threshold, the higher the rents that validators need to receive in order to keep validating. Another essential trade-off regards the level of productivity in the system. There is obviously a first best allocation, which is where the marginal gain of X is such that it equals the marginal cost of producing it. But we find that neither with the central validation nor with the decentral one, the first best allocation can be obtained. Rather, the incentive constraints always bind, and the optimal allocation balances the various incentive and participation constraints to achieve the second best. If we take all of these insights together, we find that when agents are future-looking, when cheating gets caught easily, it is easy to discipline behavior, and the central intermediary is the optimal outcome. When preferences are such that it is very hard to incentivize honest behavior, there is actually a case for decentralization. It could even be so far that we have perfect decentralization, that every late producer is also a validator. And there is also a case, of course, if agents are extremely myopic, there is no validation protocol that can sustain exchange. So let me conclude. As BIS General Manager Augustine Karsten had put in a speech at Princeton University about a year ago, money is a social convention, but what is crucial are the institutions that support this convention and ensure the trust and the stability of money's value. Today, I've investigated whether the permission variant of distributed ledger technology can help in supporting this institutional arrangement, and the answer is a generic yes. In fact, we do find that it is especially in settings where cheating is profitable that DLT may have a role. We also make some predictions regarding the optimal design, what is the optimal remuneration of validators, what is the optimal voting rule, and what is the optimal number of validators. I did not have the time to go through all of these results, but I still hope to have convinced you that this paper shows what the fundamental economic advantage of the technology is, and I very much look forward to any questions you might have on the paper. So thank you very much, and let me stop sharing. And maybe there were some questions. Should I answer them from the chat, or do you want me to? Do you want to moderate?
Oh, yes. It's up to you. I guess we have only one question that was from Anya, but I'm not sure if this Anya, if this question is for Raphael or is it for Jeff? But Raphael, feel free to take this question.
Okay, so wait. I have Andrea. I have.
Would you be able to see?
Yeah,
let me read it. Let me read it out then. Existing payment networks and systems rely on payment standards and formats such as SEPA's /SWIFT framework, ISO 20022. How can a CBDC fulfill these payment standards? That was a question posed at the beginning of the presentation.
There were for Jeff. I can answer them still. I guess we should keep in mind why existing payment networks are not yet based on ISO 220, right? And it's a very big effort to move them there. And the advantage of CBDC would be that we're designing them from scratch with a common standard in mind, right? I think it's a question about legacy system, and CBDC must not be held back by legacy standard. I think that's the answer here. There is a question on permission and permissionless be joined together. And I think that's a very interesting point. Obviously, right, and if you talk to people on coming from any sort of institution with a record, then they would say we don't need that because the permissioned version is all we need. But I feel there is kind of a value, right, in the sense that a letter that is stamped not only by some authority, but also by a little proof of work that shows that somebody put in some economic effort into sort of just demonstrating this was said at a certain point of time, and I burned a certain amount of money to prove it. Not a vast amount, but just to sort of support the consensus. I think that might be very interesting, and it could be sort of right that we can have sort of semi-trusted systems that can be supported along the combination of these two methods.